All right. Good afternoon, everyone. We're just going to give everyone just another moment to come in, and then we'll get started. All righty. I think we can go ahead and start. Good morning, everyone. My name is Christiana Allen. I'm sorry, is it morning? Good afternoon, everyone. My name is Christiana Allen. I am the Risk Communication and Learning Specialist for the Weatherwise and Vortex SE Outreach and Engagement. This is our third installment of our series, Storm Tech, the tools behind the forecast. And this episode in particular will focus on the OTUS project, which I will give you some information on them in just a second. But first of all, what is Storm Tech? Um, it is a series that we created because we believe that a deeper understanding of climate technology, the technology that's used to predict and identify storms. We believe that if people have a better understanding of that technology, they're more likely to trust the alerts that they get during those storms and respond swiftly and appropriately. So today we are featuring the Otis Project, and our speakers are Nelson Tucker and Lewis Tucker. And they will have some support from their team members, Tanner Beard and Eric Fox. They're going to explore advanced drone technology. They fly directly into tornadoes. And they will explain how UAVs intercept storms, gather critical data, and withstand the conditions of these tornadoes. And all of these things help improve severe weather forecasting and protect communities. So it's just some housekeeping before I pass it over to Justin. This session is being recorded and it will be uploaded to the Mississippi Alabama Sea Grant Consortium YouTube page. It will also be on our website as well, Mississippi Alabama Sea Grant Consortium. We will send a copy of it or a link to it to your email. And all of our Storm Tech webinars have an accompanying extension publication, which summarizes what the webinar covers, and you can pass it around. Let's see, am I missing anything? We will have a Q&A session after Lewis and Nelson present, and I'm going to send it over to you, Justin.
Okay, thank you all. Um, make sure that everything, yes. So there, I'm going to just briefly cover the bios of our speakers today and actually the wider team. So first, Nelson. Nelson is the OTUS president, and he hails from Northern Virginia. He has been a primary researcher and writer at Tornado Talk since 2020. He is studying as an undergraduate. Well, he's been an undergraduate, research fellow at the National Institute of Standards and Technology. He's in his penultimate year at Millersville University, where he majors in meteorology with minors in journalism and emergency management. After graduating, Nelson hopes to continue his studies and pursue a PhD. In his spare time, he enjoys weather photography, time-lapsing, researching, mapping, and damage analysis. Lewis, notice same surname, they're brothers, has flown drones his whole life and actually picked up drone racing in 2019. 2023 became the National Collegiate Drone Racing Champion and led his school to a first place finish in 2024. As the older brother to Nelson, Lewis learned about the challenges that researchers face when gathering data near or inside a tornado and realizing the OTUS concept was possible with the right engineering expertise to solve some of the issues. Along with Tanner, a close drone racing friend, OTUS was born, and less than 3 months, he flew his first drone inside a tornado in May 2024. Other team members who aren't here today but are really important to this project is Tanner Beard, who is the OTUS lead engineer. He's an aerospace engineer based in Brownsville, Texas, and has over 8 years experience building, flying and racing quads and fixed-wing aircraft. He's a sponsored drone racing pilot and placing second at the 2023 Collegiate Drone Racing Nationals. And his whole house is a bit of a workshop with mill lathe welders and 3D printers to create some of the tech that they're going to be talking about today. Outside of drones, Sana enjoys longboard dancing, surfing, and storm chasing. And the final key member of the team here is Eric Fox, who's a storm chaser and meteorologist. He's been chasing since 1995 and has been a field correspondent since 2016 for Weather Nation. Before being a correspondent, he was a DoD forecaster from 2010 to 2015. And Eric started the National Storm Chaser Summit in 2019 with James Menzies. I apologize. We're not chasing tornadoes and severe weather. Eric has been a police officer and has been with the force since 2010. With that, I am now going to stop sharing my screen and pass it over to the team. Thank you very much.
First of all, we're going to go through what is the OTUS project, why do we exist, what is the purpose of OTUS, the drone design and engineering challenges associated with doing what we're doing. It is an immense challenge just to chase tornadoes, let alone be able to fly drones inside of them. So that's a huge challenge that we want to talk about. Obviously, we want to talk about the data collection. Why are we doing this for science? What is the need there? And what are we actually gathering? And then we're going to talk about takeaways from field work. A lot of chasing is a complicated thing. It's not just doing this all in a vacuum with sensors and taking measurements. It's also going out and doing that in the real world and getting these intercepts. We're going to talk about what's next for OTUS, what we're looking forward to over the next few years, and just do a little Q&A at the end. So without further ado, I'm going to pass it off to Nelson.
Thank you, Lewis. So the tornado threat, I'm sure at least most of you on here are all well aware of what tornadoes are capable of and how much damage they can cause. They are a significant threat to life and property in the U.S. In the NIST Joplin report that they released in their investigation, they found that tornadoes cause more deaths on average in the U.S. than hurricanes and earthquakes combined. And in 2023, convective storms responsible for about 65% of economic losses from natural hazards in the U.S. And despite all of this, and despite many campaigns and attempts to get data on tornadoes, direct measurements characterizing the near-surface tornado environment and flow structure are still pretty elusive and incomplete. We've had breakthroughs here and there, but it really remains a very difficult part of the science and something that is probably going to be a focus still for decades and decades to come. Next slide. So that's where OTUS comes in. So OTUS originally started as a question discussion about some of these issues between me from a meteorology perspective, and then you have Tanner, of course, who's graduate with an engineering, his engineering major. So it's an interdisciplinary effort between meteorology and engineering. We created this to leverage novel drone technology that has not been used in this way before in this scientific field for tornado research. And our goal is to enhance the protection of life and property through this data collection. There are multiple ways that I'll walk through how we're plan on doing this. And we have a particular focus here on the near surface wind speed measurements to assist building standards. Next slide. And I won't read all of these words for you, don't worry, but just for the more academic-minded folks in the audience, this is just some of the original resources that we use, and we were actually coming up with talking about these issues and ultimately came to deciding to create OTUS. So there's a very common theme here. There's a lot of issues with measuring in the lowest 100 meters. There's a lot of issues with the vertical wind speeds, with how tornadoes are different than other boundary layer windstorms like hurricanes and straight line wind. And there's also a lack of instrumentation that can measure these conditions. Slide. So ground probes are previously the best or the closest we've gotten to getting some of this real world truth data. And the first ground probe that I know of was implemented in 1980. There have been many, many, many attempts over the years since then. They continue to be used. They are still an effective research tool for getting in situ data around these storms. And unfortunately, though, with all of these attempts, there have still been minimal measurements to date inside the radius of maximum winds. They're fixed once they're placed, so it's really hard to be close enough to, but still be safe and still place them in the path of the tornado that's always changing and always moving in different directions. There's been loss of life in the past, of course. This is a very dangerous thing to do. And ultimately, these are fixed measurements of maybe 2 or 3 feet above the surface where you're getting these measurements. So you can't observe tornado characteristics above that or in a particular part of the tornado you want to look at. Next slide.
Cool. And so that's where drones come in. So I had been a drone racing pilot in college, as talked about earlier, and Nelson, being a younger brother of mine, we would have conversations, over Thanksgiving or just winter breaks, weekends, whatnot. And so he knew about all the drone racing that I was doing. And what drone racing is, just in a few sentences, it's a really competitive kind of sport where you build these insanely high-powered drones that can fly up to 100 miles an hour. They can pull 20 Gs in turns. And it's very fast paced. And, a lot of drone racers are kind of on the forefront of this drone technology that's, been developing over the last decade, I would say. And so coming from this world, we realized through having some conversations with me and Nelson that, hey, this could actually be done. We could actually measure and actually fly inside of tornadoes if we're able to utilize drones that have the power requirement to be able to do so. So in order to fly inside of a tornado, our drone needs to do quite a few things. So this was all the design considerations that we made when developing this project. So it needed to be capable of sustaining controlled flight in extreme winds. So even if the drone can't fly as fast as the tornadic winds, controllability for us is everything, right? We need a stable platform to mount our sensors to, and we need to make sure that even if the drone is being overtaken by the tornadic winds, it's still able to maneuver maybe away from the tornado or get out of harm's way, and it just needs to be controllable. So in that sense, even if you can have tornadic winds that are in excess of 200 to maybe even 300 miles an hour, our drone can still be able to fly within that, assuming that there's maybe just some light debris in the air, especially, if there's trees in the air, maybe that's a little bit of a different story, but especially if we're in kind of open countryside, that's perfect for us. It also needs to be manually flown with FPV because autonomous systems, at least as of today in 2025, they're just not really cutting it. We actually put a lot of autonomy on our drone this past year to test out in the field, and it just started like doing circles, and it just was not working out very well. So it's pretty clear that in such a crazy environment underneath a mesocyclone and a supercell, it's just really, really difficult for these systems to handle what's going on in the environment. And so having a manual pilot, someone that has almost like a second nature with the drone, who's able to fly when you're not even seeing anything in the air, right? When you're inside the cloud, that's a big deal. So we needed that to be considered. And lastly, it just needed to be waterproof, right? So when you're thinking about designing different kinds of vehicles, usually you're thinking that the vehicle is traveling in one direction, right? But with these drones and in a tornado, wind and water and debris is coming from all different angles. It's coming from under you, above you, on either side. And so you have to take all this into consideration and make sure that everything is fully, waterproof, resistant to as much debris as you can, and sustain a sufficient flight time for data collection, because it's really the line between efficiency and speed. So we were trying to meet that right in the middle. So here's some pictures of me doing some building and R&D back in 2024. We came up with this project, and within a few months, I was out building drones. And at the time last year, we were using very, cheap sensors. You could have bought them on Amazon, but we just wanted to prove the point that you could have this all integrated together with the software. So Tanner helped tremendously with that work and making sure that all this was integrated. I did a good amount of the drone building, and that's kind of how we came up with the design. There's definitely a lot going on here, and it was even pretty complicated for myself. So here's the quadcopter setup that we came up with to get into more of the details. So our top airspeed is about 70 meters a second. So that's about 155 miles an hour. So even though that's maybe not as fast as tornado wind speeds if they go in excess of 200, still we were able to have that stability like I mentioned earlier. So our flight time really varies. So if you're actually flying, at your max speed, that's actually draining a lot of current. So even though that we put, the best batteries in the world that we could on our drones, still, there's so much power that is required to be able to fight these winds. The RFD, just turbulence and all this stuff. The motors are constantly having to correct for such a dynamic environment, and so that really cuts down the flight time. But if you are flying pretty easy, you can get up to 10 minutes, which for us is pretty great. Max range is about 10 kilometers, really and that's about 5 to 7 miles. It really just depends on the terrain. If we're in a really flat terrain, maybe we can have some decent range, but ideally maybe we're on a little hill. There's a lot of rolling hills out there in the Midwest. And so if we can kind of get ourselves positioned on one, that usually is really, really great for us out in the field. As I mentioned, everything needs to be rainproof. We have a robust controller, telemetry, and HD video link. So we're using a lot of different frequencies on this drone. We have a lot of different methods of data redundancy. So in fact, that we lose maybe one aspect of receiving data, we have another link that can still give us that data too. So we're running, for example, for the drone controller, we're running it on 2.4 gigahertz. The HD video link is on 5.8, which we're also streaming the data from back as well. And then we also have real-time telemetry. So if for some reason we lose control with the drone and we lose the video from the drone, we still are able to know everything that's going on board because we also have another telemetry link back as well. We put on pretty much two of the most high-performance drone racing batteries you could, slapped them together, and then put them on this drone. And we have a 3D printed modular design, which was made out of TPU filament. So it needed to be as durable as possible because, obviously when you're flying in a tornado, who knows what can happen. You want to make sure that even if the drone does happen to hit the ground, it does survive and it does keep everything intact inside. And then lastly, we're gathering a lot of different kinds of data points here. We're gathering wind speed, humidity, temperature, pressure, pretty much everything that you can to be able to understand what's going on in a tornado. And then before we move on, just wanted to say that we have worked extensively with the FAA. Obviously, this was about a year ago before the whole government shut down everything, and it took a lot of work by the team. But we were able to get a full waiver. This is probably one of the biggest waivers that I've ever seen, actually, because we had to waive so many different things to do what we're doing. So, like for example, we waived the wind speed, we waived flying line of sight. So, for every drone, it's technically not legal to fly inside of a cloud or to fly inside of a tornado. So, we have to be able to have all these things waived and approved, especially, working in academia and all that. So that's really important to us. And I'll hand it off to Nelson.
Yeah, so the timing, separate from OTUS initially, I had actually been applying as we were developing OTUS. I had already applied to the summer undergraduate research fellowship at NIST earlier in 2024. So after our first mission, literally within less than a week after we were chasing and deploying, I had actually started this in person at campus. So I assisted with the database of critical facilities hit by tornadoes, some enhanced Fujita scale damage analysis, looking at some wind speeds from the National Weather Service. My mentor in this program was Dr. Mark Leviton, who is the lead research engineer for NWERP, and discussions with Mark about the OTUS stuff that I've been doing eventually led to us creating a partnership for the development of a new 3D wind sensor specifically designed for tornado measurements on drones, because you can't just stick any old anemometer on a drone. There's really nothing out there on the market that can actually do all of the things that we needed to do and survive. So we had to come up with a unique design to be able to do this. And next slide, please. And reason this works so well, but there we go. So in the strategic plan for the NWERP, the National Windstorm Impact Reduction Program, one of their key things that they're asking us for is the development of new sensors and new methods to measure wind speeds. And they have to provide insights into the variation of wind speeds with height. In addition to just your ground observations, drones are perfect for that. There's really no other way you're going to get direct in situ measurements with anemometers and direct observations like that.
Great. And then just to hop in, so I know we've been jumping around the timeline a little bit. So we've really tried to prove this concept over the last maybe 2 years. So we, first deployed out in 2024 for about 2 weeks. And then this past year, we chased a bunch more because, even with a lot of our connections drying up in the government as of the beginning of this year, we still wanted to do this. We still wanted to move forward with the project, even if it was on our own dime. So, the timeline is that we really got this started in about maybe 2 or 3 months back in the beginning of 2024, deployed in May of 24. And then we pretty much were just networking, going to different conferences, talking to people in the field, working with NIST. A lot of our time, honestly, was spent on developing that 3D wind sensor, which is really just like developing a whole nother technology. So not exactly what we signed up for when we first started this project, but we've kind of taken upon ourselves to really spearhead that as well. And then we had another deployment from March to July. So we were out for much, much longer. This graphic here on the right shows all the chasing miles that I had. So I think I went about 26,500 miles just chasing. So in total, it's probably definitely over 30,000. And yeah, it was a lot of work. So going to take it back to Nelson, and he's kind of going to talk a little bit more about the data collection and what we're really trying to measure.
Right. So fundamentally, Otis is putting drones in locations that are either difficult or just straight up impossible to otherwise safely reach for direct atmospheric measurements. That means the sensors have to be up to par to deal with the tornado, record reliable data that is good enough for scientific usage, for academic purposes, and has to survive and collect all this data. So we talked before, we're collecting 3D wind data and thermodynamic measurements at temperature, pressure, humidity. We're focusing on that wind measurements in the near surface portion of tornadoes and in the core there. Next slide. So a big part of this was the NIST wind sensor. Initially, we were hoping with 2025 we could go out into the field with the full final design. There were a lot of delays, of course, going in 2025 and funding issues in the spring. So that was delayed. Instead, we operated in 2025 with a more usable partial 3D wind sensor to give us partial coverage, so we could at least get some measurements. And the current planning is that we're going to post calibrate some of the exact sensor used in some of our flights this year in prior tornadoes, and we're also calibrating a final wind sensor design for near omnidirectional wind measurement in 2026 with a high hertz, refresh rate, and able to collect very precise, fast-paced data on wind speed. Slide. Okay, so these are some of our wind intercepts this spring, the ones that we had the wind sensor on. We had 11 flights total into 8 different tornadoes. This was one of those tornadoes near Arnett, Oklahoma, on May 18th. We had a pretty wide range of tornado types and strengths. We had tornadoes that were a mile wide. We had tornadoes that were a few yards wide. We had all sorts of different kinds of conditions. And generally, the drones did very well with this. And we collected some really interesting data. And one thing I'm going to give a sneak preview with on the next slide is some pressure data. We're still, the final validations are still happening, but this is reasonably confident enough we can share some of this. You can play this video. This just shows some of that pressure gradient near a tornado. You can see how precise it is to how far away we are to the center of the tornado, really that frame of reference from the tornado center. Even though we're moving with the tornado in the flow, you can see how the pressure changes dramatically, just how far away we are from there with that gradient. This is why tornadoes have such incredible wind speeds. These gradients are hundreds of times stronger than and closer packed in terms of atmospheric pressure than you would even find in hurricanes, which is how they're so incredibly destructive. Another thing we had is multiple drones at once. So we don't just want one data point. As useful as that is, it's much more useful to have multiple data points at once moving around in these tornadoes so we can characterize the flows in a way that is actually really scientifically valuable. So this is an example. These are OSDs. This is what the pilots are seeing in real time as they are flying. This is what they're seeing, all the data on their screens. These drones were flying simultaneously in this tornado. This is another case. This was an anticyclonic tornado that was not fully condensated at the time. It did condensate somewhat later on. But this is just an example of these drones were orbiting around with the tornado to collect data, thermodynamic data. And then on the next slide, you'll see this is just a preview of some of the thermodynamic measurements from just one of those. This is just one of those drones of the 2 that you saw there. We're still validating these sensors, so I'm not giving exact values right now, but just some of the broad brush trends that we had in here. Of course, you had more humidity, moisture. You're in the tornado with the pressure falls, the condensation. So some really exciting stuff that we're very eager to dig into. And then also another thing, if we move to the next slide. So this view shows a structure destroyed. A lot of our intercepts are in pretty rural areas. Obviously, with tornadoes, it's easier that way. But from time to time, we do see structures destroyed, and this provides really interesting opportunities to compare our measurements and wind speed observations with the damage ratings for the enhanced Fujita scale, with the damage caused to understand some of the more nuances of the flow structure of the tornadoes, the horizontal and vertical components. So in here, you'll see in a moment, there's an outbuilding that gets just completely destroyed and blown apart here. And also another point with this too is that there's the building as it blows apart there. Another thing too is we're not just going for the really photogenic tornadoes in classic high plains tornado alley in like the Dakotas or Colorado. which is where you'll see a lot of storm chaser photos or drone shots hovering around. We're looking especially for those tornadoes that cause a lot of impact to people. So this flight right here is in Missouri near the Kentucky-Tennessee border. This is not, in that classic tornado alley, so to speak. This is the Mississippi Delta. We're really hoping to get more measurements in a lot of these different areas that you don't often see these field campaigns go as much into as they might in easier terrain. So we can gather data on tornadoes in locations that really matter to people. Next slide. And this was probably the strongest tornado we've been in. We're still have a ways to go with the NIST wind sensor calibrations, but just based on our observations of the movement of the drone, this tornado put up probably the biggest fight that we've ever had to fly into. And this tornado was very strong. This is a predecessor tornado to the Enderlin EF5. So this tornado occurred in nearly the same environment as that. This one did not hit as many houses as Enderlin, but it was probably also very, very strong. It was rated a higher end EF3. But again, you never really know the higher end of these tornadoes, given how rural this area was. There weren't a lot of damage indicators, but this was the real-time view from our pilot trying to punch through that tornado. A lot of signal interference. It was a very, very strong tornado and one of their final intercepts of that year. We can go to the next slide.
All right, so some key takeaways. We had a pretty crazy year. We intercepted about 11 tornadoes, and we just kind of wanted to rehash. What did we do well? What can we do better? And so what we've realized is as great as this project is, and as much potential drones have, doing this on our own shoelace budget, that definitely leads to a few different inefficiencies. So in terms of deployment, for example, we have to position ourselves in a very strategic place to be able to do these launches. Ideally, we're in the inflow, so that way the drones actually carry to the tornado. But sometimes we'll end up on the southern side or the western side or eastern side, and so that can lead to a lot of different challenges. So we're still trying to optimize how do we chase in the best way possible. Dealing with geography is a big issue. So if you don't have line of sight with the drone in terms of the controller link, then you're not really going to be able to have really good connections. So for us, it's also how do you position on the right place in the storm, but then also how do you position yourself on the right place geographically. So like sometimes we've even just like pulled up to topographic maps to be like, okay, where exactly should we be? We've also had a lot of video signal issues. So, there are other people that are also trying to fly their drones out there. And that's been a pretty big issue for us, just because the frequency band is so narrow that, at least for our channels, they can become crowded very, very quickly. So actually in that last flight that we had, we think that we had like a video signal issue, and there was overcrowding on the frequency. So that's why that we ended up losing that drone. That's the only drone that we've actually lost so far. We also, again, don't have 3D wind sensing. This is something that we are working on. We're doing our best to carry out, but it's incredibly complicated. It's like developing a whole new technology. So we're really just trying to spearhead this with NIST and see how that goes. But obviously, it's been a very, very slow process. And then also, storm chasing is incredibly taxing. So as I kind of alluded to with showing the documentary, like we really want to show people what are the realities of doing this kind of science, but also just like all the miles that you travel in a vehicle. Usually when you're chasing, peak tornado time is maybe around 7 p.m., let's say. I'm not actually the expert here, but from what I know, it's around that time. And so you pretty much don't eat dinner unless maybe you get back to a gas station at midnight. So there's definitely ways that it's pretty taxing, stuff that you don't usually see online, or you see what people are talking about. But I mean, just, the amount of miles that we go, I think we went about 650 miles a day per chase day. So if that puts anything into perspective. And then also just talking about the realities of being a pilot. We had a question about this before we started our presentation, so we wanted to address that. There's really no guarantee of success. Getting to the tornado is difficult enough. Especially working with Eric Fox, that has been so helpful for our team because we really want to be working with professionals that have decades of experience, because storm chasing in itself is an art. And there's just so much that goes into actually narrowing down where exactly do you need to be. With our drones, we need to be within 5 miles in order to actually deploy. But if you're just a more regular storm chaser, then you can be, maybe 20 miles away and it's not that big of a deal. So for us, we really have to position ourselves very close, but also be relatively safe. And obviously, it's not as close as deploying a ground probe. So that's why, in our opinion, it's definitely much safer to do what we're doing, but we still have to be relatively close. And given the amount of roads, that we're dealing with out here in the Midwest, it could be a challenge to find the right route. Hail is a huge challenge for us. So actually, just after this photo, as you can see here on the right, I had to put on a hard hat. And that video actually that we saw of the pressure, going up and down during that flight, there's baseball size hail like falling around me, and I'm outside with a little hard hat on, uh, trying to keep my cool. And yeah, so that's a huge challenge. That was really scary because what we're doing for Tanner and I being the pilots, we're pretty much trusting Eric and Nelson with our lives, as we're driving up to the tornado, and then we kind of put on our VR goggles, and it's kind of like that you're just blindfolded, right? Like you hear everything that's going on, but you don't actually see what's going on unless you're actually, in the action with the drone. So yeah, it's a whole new world. Also, limited daylight is an issue. As I mentioned, 7 p.m. is around peak tornado time, but you do get a lot of tornadoes after dark. So we actually deployed a night vision drone this year that did intercept a tornado. So that was the world's first night vision drone intercept. And we've had a little bit of success with that, but the technology is so new, especially on the night vision side, that it was pretty inefficient. We only had one quad, and so actually, had we been able to have multiple night vision drones this year, we may have potentially even gotten data on the Enderlania 5 tornado. But unfortunately, we weren't able to do that because the tornado before it, we'd flown into, and then the drone landed, and we had to go get it and find it, and that took a little while. So also, power management's a big deal. We're drawing a lot of current on the drone, but also in the vehicle. We have to set up an inverter that's able to, take the alternator's power and be able to convert it into everything that we need. So, we're running many different monitors and computers and drone chargers, controllers. There's so many different little batteries that you need to keep track of. For example, the battery in this picture that's, strapped on my head with the goggles. Like if any battery does not work, or if any battery is not charged when you're ready to go, that can be a big issue. So that's just like a lot to keep track of. And then, as I mentioned earlier, video interference is obviously a big problem for us. So for us, we're just trying to make our connection as strong as possible. We're gonna continue to do that this next year. Try to be able to have antennas that can really directionally point on the drone, and then that way, we're not able to have as much interference issues. So with that, I'll pass it back to Nelson.
Thank you, Lewis. So there's a lot of different applications and avenues we're exploring with OTUS. So a lot of different ways we're trying to benefit everybody in general. As we've talked about before, some of the disruptions on the government side have really delayed pretty dramatically the wind sensor aspect of it. So we're really doing everything we can to make sure that 2026 will have an omnidirectional wind sensing. And we are pretty confident, at least, that we will be able to go back and analyze some of the wind data we've already collected and get some really exciting observations. I mean, we record wind data at a very high rate, about 50 times a second. And we're hoping we can get some really interesting observations from that. And in future, kind of coming into this next tornado season, we're going to be doing some bigger like wind profile analyses with bisections of tornadoes. Some of the graphs I showed you before, we were orbiting with the tornado flow inside that radius maximum winds just to try and get some more stable thermodynamic measurements. But we're also hoping to really get some good bisections of tornadoes to get full slices. Similar if you've seen some of the Hurricane Hunter flights, that's some of the stuff we're going to be doing with multiple drones at a time, at different heights, to characterize that flow pattern, that vertical variability. We've assisted with several damage surveys for tornado documentation. Some of it has been from our drone flights, showing where tornadoes actually started and ended in some of these areas, where they actually went, what they were hitting, what was straight line wind, and what was actually tornado wind caused. We were able to show that with some of our video and some of the damage caused. And we're pursuing pretty much every avenue we can for academic partnership and collaboration for future research. We've talked with the flexible array of radars and mesonets with Josh and Karen there with the Doppler on wheels, the DAOs. They have been partnered. If you saw that radar image before on the right, that was our first tornado intercept where we were actually tag teaming with them and were able to prove that first drone intercept and win, so about 170 miles an hour there. And another thing we're exploring is photogrammetry. So there's a lot you can do with photogrammetry, especially if you have multiple drones at once and you have complete characterization of their position and angles of their state estimation at the time. You can use those two cameras to get some really interesting mapping the of all of the little debris and dirt that's being flung around in the tornadoes. So we're going to be doing that. In future, we're going to have 360 cameras on our drones to better characterize these things. Our validation of our thermodynamic sensors is currently ongoing, so that's something we're going to be working on for the near term. There's also a big interest in social science. So there's a lot that we can show with our videos beyond just, oh, that's cool, that's a tornado video. That's not really the point. So we want to actually showcase to people some of these dangers to the general public in a way they can understand. So one thing that a lot of people in the public do not understand very well is that tornadoes don't have to be condensated to be incredibly destructive. A lot of the damage we saw in our flights was from non-condensated tornadoes with very strong winds. And we think this is a really great way to show it from an aerial perspective. We can also show rain wrap tornadoes. We want to show, especially in the deep south, where you don't have, there's not many storm chasers there. There's not as many views of tornadoes there. We really want to show why you shouldn't go out on your porch and try and look for the tornado when you get a tornado warning and the tornado is rain wrapped, and show like when we go through these rain curtains, there's a tornado on the other side of that. That's what could be hiding in the rain. That's why you need to be taking this seriously. And just because you don't see a tornado doesn't mean it isn't there. So this is something that we are very much interested in showing that aspect. Next slide. So in recent months, we've spent hundreds and hundreds of hours on just sensor work developments, both the past sensor data and calibrations and the future. We are running tests on our temperature, pressure, relative humidity sensors to isolate our variables for validation. We're thinking in early 2026, we should be able to share some of our more exact data findings and numbers on some of our things. Next slide. So this is just a recap of some of the things I've already talked about here. We're really looking at both the several aspects here. There's structural resilience and building standards characterizing the flow of tornadoes, especially in those near surface and those lowest 50 to 100 meters, and understanding the tornado intensity, structure, evolution, tornado genesis, the thermodynamic aspects that help us both forecast and predict tornadoes better, issue better warnings so we understand what this environment means when tornadoes will and won't form. So we're increasing our efficiency by applying our lessons of previous seasons. We've had a lot of experience by this point with drone flights. We have learned so much information about how to efficiently conduct these operations that we could never have learned without going out into the field. So we have a lot of ways we're improving. We are trying to collaborate with everyone we can to work through this to make sure our data is useful. And hopefully we'll have a report with NIST out at some point on our wind sensor development and publish some of our findings. I'll turn it over to Lewis.
Yeah, so this is just like a little sneak preview. As I mentioned earlier, we've done this all out of our own pocket, and just with how much that is cost, we are looking for other streams of revenue to actually make this sustainable. So as I mentioned earlier, we're going to work with the documentary. We will probably be launching a Kickstarter pretty soon. Again, not too many details on this yet. As soon as we can kind of finalize some things on the back end, but yeah, just be aware that we are going to be trying to make a little bit more of a push, this next year to be able to to keep doing what we're doing. We also have a YouTube channel where we post all of these videos. So everything that you guys saw today is on our YouTube channel. We have all of our full flights on there, so feel free to check it out. I'm going to have a QR code right here on this next screen to where you can actually go and actually visit the channel. So yeah, feel free to take a look at those videos. Feel free to reach out to us as well. And yeah, let me know if you guys have any questions. Thank you.
Alrighty, if you have any questions, please drop it in the Q&A box at the bottom of the screen. We definitely want to hear from you. If there's any other information that you would like to know. I'll start with a question, Lewis and Nelson. What advice would you give to someone who is interested in going into this field?
Well, I think so. That's a very interesting question because I think for me personally, I still feel like I'm, even though I've done all of these things and I'm analyzing these data sets, I'm actually still an undergraduate student. So right now I'm in looking for graduate research opportunities right now, which is a very difficult thing in the current environment. But yeah, I think for people who are aspiring to do this research, definitely focusing on your studies, of course. I mean, that's cliche, but it is important. You do have to get through some of that math at schoolwork. It does have to. It is important eventually. It's not meaningless. So that's one thing. I think reaching out, like talking to people, talking to experts, learning what is important right now in the field. What are we looking for? What are the big questions that are right now that we're asking, that scientists are seeking out? Understanding what is your niche. So what is your like special like focus on this? A big thing that people look for is having both a diverse like set of skills, being able to um, do a lot of different things, not just like data analysis, but also being work with instrumentation, calibrations, all of these things, and also having specialized focus and having really just if you're passionate and you have all of these things, then you're in a pretty good place. And there's a lot more opportunities than it can often look like on the surface out there. So getting into research, just reaching out to people is really the biggest thing. Learning to connect. I mean, a lot of us, on the research side, we're nerds, we're introverts, we're not always the biggest people talkers, but that's really important is to reach out and connect with professionals and to learn from them.
Gotcha. Great advice. We have a few questions in the Q&A box. First, we have Robin, and they asked, what kind of response times do your thermodynamic sensors have?
So that is a good question. So that's varied a little bit over the years. I know a lot of our measurements are generally between 10 and 50 hertz for some of the different sensors going into I think 2024, 2025. Lewis, unless we've changed some of our setup going into the next year, I don't know if you have any more updates on some of those measurements.
Yeah, so what's kind of difficult about this is that the GPS update frequency is set, and so if we're able to even measure more than that, it's hard to kind of timestamp everything and then have it also linked to an actual location. So that's why it's a little bit difficult for us to kind of figure it out. But yeah, I mean, we're trying to work through that. Ideally, we're getting hundreds of different, kind of refreshes a second, and we're able to really understand, turbulence and what's going on at more of that micro level. But it's definitely been something that we're working on. I will tell you that, we are using the fastest response time sensors that I think that we can get our hands on at the price. So that is definitely up Tanner's alley. It's unfortunate that he couldn't make it today, but yeah, feel free to ask us or email us if you need any other help
Yeah.
on that one.
I'm fairly sure with temperature and ultimate humidity, it's at least 25 hertz right now. But that could
Yeah.
be, I think that may have been capped earlier from some of those other issues. So we could be
Mhm.
increasing that. Yeah.
Okay. And I have two from Savannah. They asked, I have been looking for, well, they stated, I have been looking for tornado damage to sector specific transportation. Then they said the types of separations of debris is quite difficult. What about asset management for sectors beyond buildings from the drone image analysis?
So sorry, can you repeat that question? So we're looking for things beyond buildings, basically. So
What about
debris.
asset management for sectors beyond buildings from the drone image analysis? Asset management, I'm not sure. I'm not
I'm
100%
not
sure what
I
they're
mean,
at.
there's a few things I can say. I'm not completely sure if I'm understanding this right, but if we're talking about different debris types, I mean, there's a lot going on in the air. So I think the one video you've seen of the Arnett tornado, for example, you see a lot of leaves going by. That's actually I think that's hemp plants. That was a hemp field that tornado was chewing through. So there's a lot of different stuff in the air, a lot of different debris. I'm not really sure. So for asset management, I'm not completely sure what that means.
And Savannah, if you want to type something else just to clarify a bit, we would be happy to answer. We have a couple of questions from Logan. Um, and he says, as a long-term drone pilot, sorry, these words are little. As a long-term drone pilot, experienced storm chaser, and tenured National Weather Service met. This has been quite interesting. In preparation for this talk, I did a bit of research as the most interesting aspect for me personally might be the logistics regarding the FAA waivers. These were a bit tough to track down. Are you all operating under the 107W 2024 03730 COW associated with Mr. Beard?
That's right. Yep.
Okay.
Yes. And I should add too, those waivers, those took a lot of work. That took, I think from the process of beginning to getting through, that was like 6 months of just pretty grueling work and going back and forth. So that was not easy because these waivers were huge. This was probably some of the biggest that I think they've ever had, at least at the time that we submitted. So yeah, that was a lot of work.
Alrighty. And he also asked the COW amended to 107W 2025 01204 in May of this year specifically? Or did you already?
I
We'll
think it
have to
was an
follow up with
amendment.
Tana on that. I think that we did have an amendment. I think it was just to verify that we were able to fly at night. So I think technically you don't even need a waiver, but we just wanted to go ahead and make sure that that was all clear anyways. So I believe that's what's about, but you may have to reach out and then you can talk with Dana on that
I
one.
I think it was because we had our that was admitted in May, and then June we had our first night vision successful flight. Yeah.
Okay. And Logan said you answered his question sufficiently. And he said, I could imagine I had one of the first 20 daylight waivers in part 107. Um, Savannah left another question. Asset management objects, and I think they're defining asset management, objects and physical things that can be tracked. Example, asset in transportation varies from traffic signals and signs to bridges and etc. The asset management tracked the inventory that an image analysis can help identify or confirm what has taken away.
So I think I might understand a little bit more. So you're talking about and basically, and sometimes if I'm understanding this right, is this referring to some of the photogrammetry aspects or
Yes, I,
um,
probably so because they mentioned drone image analysis in a previous question.
yeah. So like that's something we might be doing with so like that building we showed before that was blown apart. So tracking the debris. So there's that it is a difficult thing. That's something we're still kind of early on in our research. We're kind of more in the outreach part. We're trying to connect with some better experts on this. I mean, there's some analysis we've already done ourselves, but ideally we want to connect with people who are, you know, true professionals in that specific area. So yeah, that's something
Yeah,
we're still pretty
Nelson,
early on with.
I do think that someone did reach out to us after Higgins, and we actually gave them our video because they were doing like a damage survey on where stuff had traveled and whatnot, right? And they needed our video. So, I mean, that could maybe be what she's talking about. But yeah, we've definitely, we're definitely working with those kind of people too.
Okay, and they said it helps with damage estimation. If we have any more questions, we have a little bit more
Yeah.
time.
I will actually add on to that too. So sort of related, uh, some of like the curvature. So you have crop flattening marks with tornadoes. Something we have noticed on a few of our intercepts is we can kind of see that being made in real time. I know that there's ways you can estimate wind from some of the cycloidal markings there. So that's another thing that might be interesting to look at as well.
Okay. Alrighty, while we're waiting for some more questions in the chat. Oh, I think we have a new one from Steve. He says, what technology do you see informing tornado research 5 to 10 years from now? What's on the horizon?
Yeah, so it
Yeah.
is kind of an interesting time for tornado research. I do think drones are are only, I mean, Lewis could probably tell you more better than me, but drones are getting cheaper and easier to mass produce by the day. I mean, right now, like the automated, like the artificial intelligence is not sufficient to fly in these kinds of environments at all. We tried it and it did not go well. So we know that it's nowhere near that yet, but 5 to 10 years from now, it easily could be. That stuff is advancing very fast with AI. So in the future, I think one day you'll see much more like higher quantities of these drones that are pretty cheap and economic and can gather data on a much bigger scale. So I think that that is something that's probably going to be in the future of meteorology for atmospheric sciences because drones they can go in anywhere you want. Like they're not just fixed to the ground. And as they get cheaper and you can have more and more of these, you can get some really amazing observations because that's one of the things in meteorology right now that we're facing is we've done a lot in recent decades to interpolate and extrapolate between our data points. But there's only so many observations we have in the world. And often there's a lot of distance between those 2 points. And there's only so much you can do to extrapolate between those points about what's actually going on. So filling the gaps in with measurements, I think that's a big thing in tornado research and just meteorology in general, getting those observations, getting more observations you can feed into these computer models and algorithms.
Alrighty. We have time for maybe one more question. If you want to go ahead and put that in the chat box. Thank you to everyone who asked the question so far. And Savannah, thanks you for responding to their question. Scott says, can you go into coordination with other in situ, SITU, like surface probes or remote sensing, like mobile radar, such as the work with Karen Kosiba, or even other more novel measurement tech?
Yeah, so there's a few things that we're currently in discussions on. So with the radars in 2024, our main thing with the radars is we were proving the concept. Our first ever flight, we had the Dows there. We were actually tag teaming with them for both the Greenfield Tornado Day in Iowa in 2024, and then again on the Duke, Oklahoma tornado 2 days after that in 2024. So we were already actually pairing up with them, and the radar data was, really good validation for that. And then from there, we're actually talking about how we can integrate data and drone measurements into that with other mesonet observations. So not just like the Dallas, but also other groups like NSSL and other research opportunities. So there's so in terms of coordination, right now in our previous experience, we do have like some real time like chats back and forth, and we'll coordinate our positions and exchange those to make sure intercepts maximize these opportunities. But yeah, we're really looking forward, I guess, especially to the future and what more we can do there.
All right, last one, and I'm gonna go really quickly because we only have about 3 minutes left. Logan has a few more questions. He says, I would presume you guys understand the intrigue, given how difficult it has been to acquire waivers, never mind the numerous in one application. Do you guys typically fly from a parked or stopped position, attempting to interpret line 23, page 7 of 8 of the COW? It seems to suggest that the maximum flight distance is 1.5 statute miles. Is that sufficient to reach your targets? Also, the height restraint still 499 feet, or maybe
Yes.
400.
Yeah, that's right. So the high restriction is 400 feet. That is something that we haven't waived, but pretty much everything else we have covered. We do have, I believe that we do have the distance covered. I have to give it back to you on that one. But yes, we are pretty much always parked and stopped. I'm usually getting out. We usually have pretty clear line of sight, as mentioned earlier. And yeah, so we're usually trying to get pretty close to these tornadoes. But because of our setup right now, we do have to remain parked. We would like to maybe even next year or even future years to come, having like a setup on the vehicle where we could just fly from inside and we could be driving with the tornado. That would be the ideal case for us because then we could maybe even get a little bit closer, but still remain safe and mobile. So That's currently what we're planning to do, and we're going to continue to work with the FAI on that.
Awesome. That is all the time we have for questions. Um, okay, we have one more. Is this planned to be integrated with emergency warning systems? This would be helpful information for disaster emergency responders. If you can answer it really quickly.
Well, so yeah, I think there's still a bit of a road to get there. I mean, if we can share in real time some of our data with some emergency management managers or the National Weather Service, I mean, we have actually done that with the National Weather Service before. But in terms of emergency warning systems, yeah, so like I mean, like other chasers, we'll report on, tornado sightings or if conditions look like there's a tornado forming. But in terms of more advanced integration, I we have not had any connections on that yet, but that's something we hope to look into the future.
Awesome. Thank you so much. And so sorry to rush that last question, but we are at time. And I just wanted to remind you that we will send out a recording of this video as well as a extension publication summarizing the information that was included in this webinar. Be sure to keep up with the Otis Project, follow their socials that are on the screen, and also keep up with the Mississippi Alabama Sea Grant Consortium Vortex SE page so that you know what we have going on, our future webinars, and resources that we have created. Thank you all so much for joining us and be on the lookout for the next webinar.